Listening Practice, Chapter 1, Introduction to Fusion Energy 1.1 The Promise of Fusion, Unlimited Clean Energy Overview. Fusion energy, the process powering stars like our Sun, involves fusing light atomic nuclei, e.g., deuterium and tritium, to release vast amounts of energy. Unlike nuclear fission, which splits heavy atoms and produces long-lived radioactive waste, fusion offers near-zero emissions, no greenhouse gases, aligning with global climate goals. Abundant fuel, deuterium from seawater and lithium, for tritium breeding, could sustain humanity for millions of years. Inherent safety, no risk of meltdowns, reaction cease if containment fails. Case study, the National Ignition Facility, NIF, achieved a historic milestone in 2022 by producing a Q1 reaction, more energy output than laser input, demonstrating the feasibility of controlled fusion. By 2023, repeated successes underscored its potential as a baseload power source. Why it matters: fusion could revolutionize energy systems, offering a scalable solution to replace fossil fuels and complement intermittent renewables like solar and wind. 1.2 Historical milestones, from stellar nucleosynthesis to lab breakthroughs. Timeline of progress. 1920, Arthur Eddington proposes fusion as the sun's energy source. 1950s, Soviet scientists pioneer the tokamak, a magnetic confinement device. 1997, JET, Joint European Torus, achieves 16 MW of fusion power, a record unbroken for 25 years. 2022, NIF's ignition breakthrough, Q equals 1.5, marks the first net energy gain. 2023, NIF replicates success, achieving 2.5 mJ output, while ITER progresses toward first plasma. 2025. Key challenges: plasma stability, maintaining 150 million degree C plasmas without disruptions. Materials science, developing neutron-resistant materials for reactor walls. Quote, "We are replicating the stars in our laboratories, a testament to human ingenuity." Dr. Stephen Cowley, Princeton Plasma Physics Laboratory. 1.3 Global energy challenges and the role of fusion. Current crisis, climate change, fossil fuels drive 89% of CO emissions, IEA, 2023. Energy poverty, 775 million people lack electricity access, World Bank, 2023. Renewable limitations, solar/wind require storage and land, struggling to meet rising demand. Fusion's potential role, baseload power, 24/7 energy production, unlike intermittent renewables. Decarbonizing industries, high-temperature heat for steel, cement, and hydrogen production. Global equity, modular reactors could empower remote regions. Policy momentum, U.S. DOE's 2023 strategy, $1.8 billion for public-private partnerships. EU's fusion roadmap, targets pilot plants by the 2050s. China's KFEDR, aims to bridge ITER and commercial reactors. Comparison table, energy source CO emissions land use scalability coal high moderate limited solar/wind none high intermittent fusion none low base load key takeaways. 1. Fusion offers a clean, safe, and virtually limitless energy source, distinct from fission. 2 decades of R&D have brought us to the brink of net energy gain at scale. 3. Fusion could address climate change, energy security, and equity if technical and economic hurdles are overcome. Discussion questions: 1. Can fusion outpace renewables and fission to dominate 21st century energy grids? 2. How might geopolitical competition accelerate or hinder fusion's commercialization? This chapter sets the stage for the book, weaving scientific promise, historical perseverance, and urgent global needs into a compelling narrative. Let me know if you'd like to expand on specific milestones or policy frameworks. Chapter 2, The Science of Nuclear Fusion. 2.1 Plasma Physics and Magnetic Confinement. Technical Overview. Plasma, the fourth state of matter, is an ionized gas where nuclei and electrons move freely. For fusion, plasma must be heated to over 100 million degrees C to overcome electrostatic repulsion between nuclei. Magnetic confinement uses powerful magnetic fields to trap and stabilize this plasma, preventing contact with reactor walls. Key concepts: tokamaks, toroidal, donut-shaped, devices like ITER use magnetic fields to confine plasma. ITER's 2025 first plasma test aims for AQ greater than or equal to 10x energy output versus input. Stellarators, twisted magnetic coils, e.g., Wendelstein 7X in Germany, optimize stability without plasma current, reducing disruptions. 2023 advances: Spark, MIT/CFS leveraged high-temperature superconductors to achieve 20 Tesla fields enabling compact reactors. K-STAR, Korea sustained plasma at 100 million degrees C for 30 seconds, a record for magnetic confinement. Challenges: plasma turbulence, disruptions degrade confinement, AI-driven predictive models, e.g., Google DeepMind's work with TCV tokamak, aim to mitigate this. 2.2 Inertial confinement fusion, ICF lasers and implosion dynamics technical overview. ICF uses high-energy lasers to compress a deuterium-tritium, DT, fuel pellet, creating extreme pressure and temperature for fusion. Process: 1 laser pulses. NIF's 192 lasers deliver 2.05 mJ to a gold Hall ROM, generating X-rays. 2 implosion. X-rays ablate the pellet's outer layer, compressing the fuel to 100x solid density. 3 ignition. Central hotspot reaches 3 million degrees C, triggering fusion. 2023 milestones. NIF's repeated success, achieved net energy gain, Q1, in 5 of 10 shots, peaking at 3.15 mJ output, December 2023. Target innovation: diamond-coated capsules improved symmetry, boosting yield by 40%. Challenges: energy efficiency, lasers consume 300 mJ per shot, only 1% converted to fusion energy. Scalability: NIF single-shot design contrasts with continuous power plants. Comparison: parameter magnetic confinement inertial confinement confinement time seconds minutes nanoseconds energy density moderate extremely high reactor size large, ITER, 30 m tall, compact 2.3 fuel cycles, deuterium tritium versus advanced fuels deuterium tritium, DT, pros: lowest ignition temperature, 100 million degrees C, high cross-section, cons: tritium scarcity, half-life 12.3 years, neutrons damage reactor walls. Tritium breeding, lithium blankets in reactors, e.g., ITER, breed tritium via neutron capture. Advanced fuels, proton-boron, PB, pros: aneutron, no neutrons, direct energy conversion. Cons: requires 1 billion degrees C, TE Technologies Copernicus reactor targets PB by 2030. Helium-3, He-3, pros: low radiation, mined from lunar regolith, long-term goal. Cons: rare on Earth, needs He-3 reactions at 200 million degrees C. 2023 developments: Helion Energy, scaled He-3 prototypes for pulsed magnetic compression. LPP fusion, pursuing PB in dense plasma focus devices. 2.4 Overcoming the Lawson criterion, density, temperature, and confinement time Lawson criterion, for net energy gain, the product of plasma density, N, confinement time, tau, and temperature, T, must exceed, \n tau T3 times 1021 text kev s/m3 approaches, magnetic confinement, high tau ITER aims for tau 6 seconds. Inertial confinement, high NNIF achieves N10 superscript 3 superscript 1 m superscript 3 during compression 2023 progress, Spark, Targets n tau t2 times 10 superscript 2 superscript 1 kev s/m superscript 3, nearing break-even. Zap Energy's Z-Pinch, achieved T3 kev with tau 1 μs via pulsed power. Challenges, trade-offs, high density, ICF, versus long confinement, tokamaks. Materials, neutron-resistant tungsten alloys, e.g., ITER's diverter. Key takeaways: 1. Magnetic and inertial confinement offer distinct paths to meeting the Lawson criterion. 2. DT remains the near-term fuel, while advanced fuels promise cleaner, harder to achieve reactions. 3. 2023 milestones, NIF, Spark, highlight accelerating progress toward practical fusion. Visual aid suggestions, Figure 2.1, tokamak versus stellarator magnetic field lines. Table 2.1, fuel cycle comparison, DT versus PB versus DE3. Graph, Lawson criterion curves for major fusion projects. This chapter balances foundational science with cutting-edge advancements, providing a roadmap for understanding fusion's technical landscape. Let me know if you'd like deeper dives into specific reactors or fuel cycles. Chapter 3, the National Ignition Facility, NIF, and 2023 Milestones 3.1 NIF's laser-driven fusion, how it works. The National Ignition Facility, NIF, located at Lawrence Livermore National Laboratory, employs inertial confinement fusion, ICF, to replicate the extreme conditions of stellar cores. Here's the process: 1 laser array, NIF's 192 high-energy ultraviolet lasers converge on a gold-plated Hall ROM, a cylindrical cavity, delivering 2.05 megajoules, mJ, of energy in billionth of a second pulses. These lasers are amplified through a series of glass optics, making NIF the world's most energetic laser system. 2. X-ray conversion, the lasers heat the Hall ROM's interior, generating a bath of X-rays that uniformly irradiate a deuterium-tritium, DT, fuel pellet, 2 mm in diameter. 3. Implosion, the X-rays ablate, vaporize, the pellet's outer shell, causing a rocket-like implosion that compresses the fuel to 100 times solid density, creating pressures exceeding 100 billion atmospheres. This compression heats the fuel's core to over 100 million degrees C, triggering fusion reactions. 4. Ignition, a self-sustaining burn wave propagates outward, releasing energy as helium nuclei, alpha particles, and neutrons. Key challenge: only 1% of the laser energy converts to X-rays, and even less drives implosion. Despite this inefficiency, NIF's 2023 breakthroughs proved the viability of ignition physics. 3.2 2023 breakthrough, repeated net energy gain, Q1, technical details, energy yield. In 2022, NIF achieved Q1.5, 3.15 mJ fusion yield versus 2.05 mJ laser input. By December 2023, repeated experiments yielded up to 2.5 mJ, Q1.2, demonstrating reproducibility. Reproducibility, 5 of 10 shots in 2023 surpassed break-even, Q1, a critical step toward reliable ignition. Improved target symmetry via diamond-coated capsules reduced instabilities, boosting success rates. Scalability, while NIF's single-shot design isn't a power plant, the results validate fast ignition principles for future reactors. Case study, December 2023 shot, 2.5 mJ output, experiment overview, target design, a diamond-coated DT capsule replaced plastic, enhancing implosion symmetry. Laser precision, AI-optimized beam timing reduced energy loss by 15%. Diagnostics, neutron detectors confirmed 10 reactions, with 80% alpha heating efficiency. Implications, scientific validation, proved that alpha particle heating can sustain the burn wave, a milestone for self-sustaining fusion. Path to energy gain, scaling to Q10 requires higher laser efficiency and advanced targets. Challenges ahead: energy efficiency, NIF's lasers consume 300 mJ of wall plug energy per shot, future reactors need 10x higher efficiency. Target production, each diamond-coated capsule costs $50,000, mass production is critical. Key takeaways, NIF's 2023 successes mark the first reproducible net energy gain in fusion history, validating ICF as a credible pathway. Diamond-coated targets and AI-driven optimizations were pivotal, though scaling to commercial reactors demands breakthroughs in efficiency and cost. Visual aid suggestions, Figure 3.1, NIF's laser array and Hall-Rom cross-section. Timeline, NIF's milestones, 2022-2023. Table 3.1, 2023 shot metrics, energy in/out, Q values, target materials. Quote, NIF's results aren't just a scientific triumph, they're a beacon for the entire fusion community. Dr. Kim Budile, Director of Lawrence Livermore National Laboratory. This chapter underscores NIF's role in bridging theoretical fusion science and practical energy solutions, setting the stage for discussions on commercialization and global collaboration in later chapters. Let me know if you'd like to explore specific technical nuances or policy implications. Chapter 4, Tokamaks and Magnetic Confinement. 4.1 Adhere, Progress Toward First Plasma, 2025, and Beyond. Overview, ITER, the International Thermonuclear Experimental Reactor in France, is the world's largest tokamak project, involving 35 nations. Its goal is to demonstrate fusion's feasibility by achieving AQ greater than or equal to 10x energy output versus input, and sustaining plasma for up to 500 seconds. 2023 Progress, Construction Milestones, Assembly of the cryostat, vacuum chamber, and toroidal field coils is 95% complete. The first superconducting magnets, capable of 13 Tesla fields, were installed in Indiana late 2023. Deuterium tritium, DT, timeline, first plasma, hydrogen, remains slated for 2025, with DT experiments delayed to 2035 due to supply chain and funding challenges. Technical innovations, superconducting magnets, niobium tin and niobium titanium alloys enable stable plasma confinement at 150 million degrees C. Diverter design, tungsten-coated components handle extreme heat fluxes, 10 MW/m superscript 2. Challenges, cost overruns, budget now exceeds €22 billion, triple initial estimates. Complexity, integrating millions of components from global suppliers. Future, demo, ITER's successor, a prototype power plant targeting net electricity by 2050. 4.2 Spark and high-field superconducting magnets, Commonwealth Fusion Systems, Overview, Spark, developed by MIT's spin-off Commonwealth Fusion Systems, CFS, is a compact tokamak leveraging high-temperature superconducting, HTS, magnets to achieve stronger magnetic fields, 20 plus Tesla, in a smaller footprint. 2023 advancements, HTS magnet breakthrough, CFS tested a 20 Tesla magnet in 2021, paving the way for Spark's 2025 completion. Design finalization, Spark's 65 MW heating systems aim for Q2 by 2026. Technical edge, size reduction, Spark's 3-meter plasma radius versus ITER's 6 meters, enabled by HTS tapes, Revco, cooled to 20K. Modularity, targets rapid iteration for commercial scalability. Challenges, heat management, managing 250 MW of fusion power in a compact design. Regulatory hurdles, licensing first-of-a-kind components. Impact, timeline, full operation by 2028, ARC, a 250 MW pilot plant, proposed for 2035. 4.3 Stellarators, Wendelstein 7X and optimization of stability. Overview, stellarators, like Germany's Wendelstein 7X, W7X, use twisted magnetic coils to confine plasma without requiring a toroidal current, avoiding tokamak instabilities. 2023 achievements: steady-state operation, W7X sustained plasma for 30 minutes at 2 MW heating, a record for stellarators. Optimized coils, AI-designed coils reduced neoclassical turbulence by 50%. Advantages over tokamaks: stability, no risk of plasma disruptions from current-driven instabilities. Continuous operation, suited for steady-state power plants. Challenges: complex construction, W7X took 19 years to build, costing €1 billion. Lower plasma pressure, achieves beta 5% versus tokamak's 10%. Future: Helios design, a larger stellarator, Helios 5B, proposed for net energy gain by 2040. Key takeaways: ITER, a proof of concept for large-scale fusion, albeit delayed and costly. Spark, compact, HTS-driven design accelerates timelines for commercial viability. Stellarators, offer stable, steady-state operation but face engineering complexity. Discussion questions. 1. Can Spark's HTS innovation render ITER obsolete, or will both projects complement each other? 2. How might stellarators address energy storage challenges compared to tokamaks? 3. What global policies are needed to balance competition and collaboration in fusion research? Visual aid suggestions, Figure 4.1, tokamak versus stellarator magnetic field geometries. Table 4.1, ITER versus Spark versus W7X, size, magnets, Q targets. Timeline, fusion roadmap from ITER, 2025, to demo, 2050. This chapter highlights the diverse approaches to magnetic confinement, emphasizing innovation, challenges, and the race to commercial fusion. Let me know if you'd like to explore specific engineering hurdles or policy dynamics. Chapter 5, Alternative Approaches to Fusion 5.1 Z-Pinch and Plasma Jet Innovations, Helion Energy, Zap Energy, Technical Overview, Z-Pinch, Zeta-Pinch. Fusion compresses plasma using a powerful axial current, generating a magnetic field that radially implodes the plasma column. This creates extreme temperatures and densities for fusion. Helion Energy approach combines pulsed magnetic compression and field reversed configuration, FRC. Two FRC plasmas are collided and compressed by magnets, heating them to fusion conditions. Uses deuterium and helium-3, DE3, fuel for aneutronic reactions, minimizing neutron radiation. 2023 milestones, achieved plasma temperatures of 100 million degrees C in their Trenton prototype. Signed a power purchase agreement with Microsoft to supply fusion-generated electricity by 2028. Advantages: modular, truck-sized reactors. Direct energy conversion, no steam turbines. Challenges: sourcing helium-3, plans to breed it from deuterium. Scaling to net energy gain, Q1. Zap Energy approach, sheared flow stabilized Z-Pinch stabilizes plasma instabilities using sheared axial flows. Simpler, lower cost design without magnets or lasers. 2023 milestones, demonstrated 200 Ka plasma currents in the Fuse-Q device, sustaining stability for 5 milliseconds, partnered with Chevron to explore industrial decarbonization applications. Advantages: compact, linear reactor design. Fast development cycle, months versus decades. Challenges: achieving sufficient confinement time and density. 5.2 Magnetized target fusion, general fusion, technical overview. Magnetized target fusion, MTF, merges magnetic confinement with rapid mechanical compression. General fusion's approach: 1 plasma injection, a compact toroid of deuterium-tritium plasma is magnetically confined. 2 compression, a wall of liquid metal, lithium lead, is collapsed via pneumatic pistons, compressing the plasma to fusion conditions. 3 energy extraction, heat from neutrons is absorbed by the liquid metal, driving a steam turbine. 2023 milestones: completed construction of the LM26 demonstration plant in the UK, testing compression systems at scale. Achieved plasma lifetimes of 10 milliseconds in pre-compression tests. Advantages: inherent tritium breeding via lithium in the liquid metal. No need for superconducting magnets or high-power lasers. Challenges: synchronizing piston-driven compression with plasma stability. Managing liquid metal erosion and neutron damage. Comparison to mainstream approaches: parameter MTF, general fusion, tokamaks, ITER, compression mechanical, pistons, magnetic/inertial tritium breeding integrated, liquid metal, external blankets cost $500m, demonstrator, $22b, ITER, 5.3 private sector pioneers, TE Technologies, First Light Fusion TE Technologies, approach, field reversed configuration, FRC, with advanced particle beams. Focuses on proton-boron, PB11, fuel, aneutron and fuel abundant. Uses Norman and Copernicus reactors to achieve plasma stability at 1+ billion degrees C. 2023 milestones: demonstrated sustained FRC plasmas at 75 million degrees C for 30 milliseconds, raised $250 million in Series G funding for commercialization. Advantages: no neutron radiation, direct electricity conversion. Utilizes boron, earth-abundant fuel. Challenges: extreme temperatures required for PB11 fusion. First light fusion, approach, projectile fusion fires hypervelocity projectiles, 20 km per second, at fuel-containing targets. Shock waves compress the fuel to fusion conditions. 2023 milestones: achieved neutron yields confirming fusion in lab-scale experiments. Partnered with Nokia to develop a pilot plant design. Advantages: ultra-fast, low-cost pulsed fusion. Minimal radioactive waste. Challenges: target fabrication precision. Scaling energy gain to practical levels. Key takeaways: 1. Z-Pinch Innovations, Helion and Zap Energy prioritize simplicity and modularity, targeting niche applications like industrial heat. 2. MTF, General Fusion's hybrid approach offers integrated tritium breeding but faces synchronization challenges. 3. Private pioneers, TE and First Light pursue radical fuel cycles and compression methods, balancing high risk with high reward. Discussion questions: 1. Can aneutronic fusion, e.g., PB11, overcome its temperature barriers to become viable? 2. How might projectile fusion disrupt traditional timelines for commercialization? 3. Should public funding prioritize alternative approaches alongside mainstream projects like ITER? Visual aid suggestions, Figure 5.1, Z-Pinch vs MTF vs FRC reactor schematics. Table 5.1, Fuel cycles and neutron outputs, DT vs DE3 vs PB11. Case study gallery, Helion's Trenton prototype, General Fusion's LM26. This chapter highlights the diversity of fusion approaches, underscoring the creativity and risk-taking driving the field forward. Let me know if you'd like to explore specific technical trade-offs or market strategies. Chapter 6, Materials Science for Fusion Reactors 6.1 Plasma-Facing Materials, Tungsten and Self-Healing Alloys Role and Requirements. Plasma-facing materials, PFMs, must withstand extreme heat fluxes, 10 MW/m superscript 2, particle bombardment, and thermal cycling. Key properties include high melting point, thermal conductivity, and low tritium retention. Current materials, tungsten, W dominates due to its high melting point, 3422 degrees Celsius, low erosion and resistance to neutron damage. Used in ITER's divertor. Carbon-based composites, lightweight and thermally shock-resistant but prone to chemical erosion and tritium retention, phased out in modern designs. Challenges: brittleness, tungsten becomes brittle under neutron irradiation, risking crack propagation. Thermal stress, repeated heating/cooling cycles cause fatigue. Emerging solutions, self-healing alloys, nanostructured tungsten, engineered with grain boundaries that inhibit crack growth. Smart coatings, vanadium or chromium layers that oxidize to fill microcracks. Liquid metal diverters, gallium or lithium films that flow to repair erosion, tested in DIIID tokamak. 2023 milestones, Eurofusion's JET, demonstrated tungsten diverter durability under 40 MW/m superscript 2 heat flux. China's East, tested lithium-coated walls, reducing impurities and improving plasma stability. 6.2 Neutron radiation resistance and tritium breeding blankets. Neutron radiation effects, swelling, neutrons displace atoms, creating voids, e.g., RAFM steels swell 2% after 100 dPa. Embrittlement, reduced ductility due to defect clusters. Tritium breeding mechanisms, solid breeders, lithium ceramics, Li-TiO, Li-SiO, in pebble beds. Neutrons react with Li6, \text Li6 plus N \right arrow \text T plus \text He4 liquid breeders, molten lithium lead, PB-Li, or flip salts, enabling continuous tritium extraction. Current materials, RAFM steels, reduced activation ferritic martensitic steels, e.g., Urifer 97, for structural integrity. Silicon carbide, SiC, composites, high temperature strength and low activation, tested in Japan's TBM program. Challenges, tritium permeation, preventing leakage through blanket walls. Corrosion, liquid metals degrade steel, ceramic coatings, alloy, under development. 2023 progress, ITER test blanket modules, TBMs use HCLL, helium-cooled lithium lead, module achieved 90% tritium breeding ratio in simulations. K-Demo, South Korea SiC-based blanket design targets 1.1 tritium breeding ratio. 6.3 Cryogenic systems for superconducting magnets. Superconducting materials, NBSN and NBTI, used in ITER's 18 Tesla magnets, requiring cooling to 4K, -269 degrees Celsius, via liquid helium. High-temperature superconductors, HTS Rebco tapes, operating at 20-30 K, enable compact reactors, e.g., spark. Cryogenic challenges, thermal contraction, stainless steel cryostats must accommodate 0.3% contraction during cooling. Quench protection, sudden loss of superconductivity risks magnet damage, MIT's Spark uses active quench detection. Innovations, advanced insulation, multi-layer insulation, MLI, with 0.5 W/m superscript 2 heat leak. Hybrid cooling systems, helium gas for HTS magnets, reducing liquid helium dependence. 2023 milestones, Commonwealth Fusion Systems, CFS validated 20 Tesla Heights magnets for spark, cutting cryogenic load by 50%. ITER Cryoplant, commissioned world's largest helium refrigerator, 12 kilowatts at 4.5 K. Key takeaways. 1. Plasma-facing materials, tungsten remains dominant, but self-healing alloys and liquid metals promise enhanced durability. 2. Neutron resistance, RAFM steels and SiC composites are front-line materials, with liquid breeders advancing tritium sustainability. 3. Cryogenics, HTS magnets are revolutionizing fusion by simplifying cryogenic demands, though challenges in cost and scalability persist. Visual aid suggestions, Figure 6.1, cross-section of ITER's tungsten diverter versus Spark's HTS magnets. Table 6.1, material properties comparison, tungsten, RAFM steel, Rebco. Diagram, tritium breeding cycle in liquid PB-Li blankets. Quote, materials science isn't just supporting fusion, it's the bedrock upon which our star-in-HR dreams are built. Dr. Melanie Windridge, CEO of Fusion Energy Insights. This chapter underscores the pivotal role of materials in overcoming fusion's toughest challenges, bridging cutting-edge research with real-world engineering. Let me know if you'd like to explore specific test facilities or policy impacts. Chapter 7, Commercialization and Economic Viability. 7.1 Cost Projections, from experimental reactors to power plants. Current costs, here, Euro 22+ billion, construction and operations through 2035, funded by 35 nations. Spark, CFS $500 million, private funding, targeting Q2 by 2026. NIF, ICF $3.5 billion, construction, with $1 million per laser shot. Future power plant projections, first of a kind, FOAK $510 billion for a 500 MW plant, 2035-2040. Nth of a kind, NOK $23 billion, 2050 plus, competitive with fission and renewables. Levelized cost of energy, LCOE, 2035, $150/MWh, high capital costs, low fuel costs. 2050, $50/MWh, economies of scale, advanced materials. Comparison table, energy source 2023 LCOE, $/MWh, 2040 projection, $/MWh, coal 65 150 90 200, with CCS, solar PV 30 50 20 40 nuclear fission 70 150 60 100 fusion, FOAK, N/A 100 150 fusion, NOK, N/A 50 80 key drivers, capital costs, superconducting magnets, tritium breeding systems. Learning rate, 10-15% cost reduction per doubling of capacity, similar to solar. 7.2 Grid integration, baseload versus intermittent renewables. Baseload advantages, 24/7 operation, unlike solar/wind, fusion provides consistent power, complementing renewables. Grid stability, inertia from turbine generator systems helps maintain frequency. Hybrid systems, hydrogen CO generation, excess fusion heat splits water for green hydrogen, e.g., UK's STEP project. Thermal storage, molten salt tanks buffer energy for peak demand. Challenges, ramp rates, fusion plants may need hours to adjust output, unlike gas turbines. Transmission, siting near cities versus remote areas, neutron radiation concerns. Case study, EU's Horizon 2050 grid, models fusion supplying 30% of baseload, paired with 50% renewables and 20% storage. Comparison table, parameter fusion solar/wind natural gas capacity factor 85-95% 20-40% 50-60% scalability high, modular, moderate, land use, limited, emissions, carbon emissions near zero high 7.3 regulatory hurdles and safety standards. Unique challenges, novelty, fusion lacks a mature regulatory framework, rules for fission, e.g., NRC Part 50, are ill-fitting. Tritium management, tritium, radioactive, half-life 12.3 years, requires strict containment, e.g., double-walled piping. 2023 regulatory progress, IAEA's fusion-specific guidelines, released in 2023, focusing on asterisk-graded approach, risk-based regulation. US NRC, proposed a streamlined licensing framework, 10 CFR Part 53, for fusion in 2023. UK's Fusion Green, classifies fusion as non-nuclear, simplifying siting and waste rules. Safety advantages over fission, no meltdown risk, plasma quenches if containment fails. Low activation waste, short-lived isotopes, e.g., 100-year decay versus fission's 10,000 plus years. Key standards, tritium release limits, 1000 TBq/year, ITER's benchmark. Neutron shielding, concrete/metal composites to limit worker exposure to 1 msv/year. Case study, Commonwealth Fusion Systems, CFS worked with US NRC to pre-license Spark, targeting 2028 grid connection. Key takeaways. 1. Cost trajectory, fusion's LCOE could rival renewables by 2050, but FOAK plants require public-private partnerships. 2. Grid synergy, fusion complements renewables as a base load source but needs flexible grid architectures. 3. Regulatory innovation, simplified frameworks are critical to avoid delays, tritium and waste rules must balance safety with practicality. Discussion questions. 1. Should fusion plants receive subsidies akin to early solar/wind to accelerate deployment? 2. How can regulators balance public safety with the urgency of decarbonization? 3. Could fusion's baseload capability reduce reliance on fossil-fueled peaker plants? Visual aid suggestions, Figure 7.1, Cost reduction curve for fusion versus historical solar/wind. Table 7.1, Regulatory frameworks comparison, US, EU, UK. Infographic, Hybrid energy system with fusion, renewables, and storage. Quote, fusion won't just power the grid, it'll redefine how we build, regulate, and value energy systems. Dr. Melanie Windridge, Fusion Energy Insights. This chapter bridges the technical promise of fusion with real-world economics and policy, offering a roadmap for stakeholders to navigate its path to commercialization. Let me know if you'd like to explore financing models or regional case studies. Chapter 8, Global Collaborations and Policy Frameworks. 8.1 Adheres International Consortium, Lessons in Multinational R&D Overview. Adhere, the International Thermonuclear Experimental Reactor in France, is a landmark of global cooperation, involving 35 nations, EU, US, China, India, Japan, South Korea, Russia. Its mission is to prove fusion's scientific and technical feasibility. Key lessons: 1. Collaborative governance, shared costs, members contribute in-kind components, e.g., EU provides the tokamak, Japan the superconducting coils. Decision-making, unanimity required for major changes, leading to delays, e.g., DT experiments postponed to 2035. 2. Technical synergies, fusion engineering expertise pooled globally, e.g., Russia's Gyrotron Tech, India's Cryostat. 3. Challenges, delays, original 2016 first plasma delayed to 2025 due to supply chain and bureaucratic hurdles. Cost overruns, budget ballooned from €5 billion to €22 B+, testing the consortium's resolve. Future implications, demo successor, Adhere's model informs plans for demo, but streamlined governance will be critical. Private sector engagement, startups like CFS and Helion leverage Adhere's data but avoid its complexity. Quote, Adhere is a triumph of diplomacy, but fusion's future needs agility. Only smaller, focused teams can deliver. Dr. Bernard Bigot, former Adhere Director General, 8.2 US DOE's Fusion Energy Strategy, 2023 Update, 2023 Policy Shifts, 1 Bold Decadal Vision, Goal, Pilot Fusion Plant delivering electricity to the grid by 2035. Funding, $1.8 billion allocated via the Fusion Energy Sciences Act, prioritizing public-private partnerships. 2 milestone-based grants, Infuse Program, $50 million awarded to startups, e.g., Zap Energy, TE, for neutron-resistant materials and tritium breeding. 3 Regulatory modernization, streamlined licensing under the Nuclear Regulatory Commission, NRC, treating fusion separately from fission. Key initiatives, ARPA ES Beta Program, $100 million for advanced fusion fuels, e.g., PB11. National Laboratory Partnerships, Princeton Plasma Physics Lab, PPPL, collaborates with CFS on Spark diagnostics. Challenges, tritium supply, U.S. lacks infrastructure for large-scale tritium production. Workforce gaps, DOE estimates need for 20,000 fusion engineers by 2030. Quote, the US is betting big on fusion not just for energy, but for global leadership in a post-fossil world. Dr. Kathleen Hogan, DOE Undersecretary 8.3 China's FEDRA and the race for fusion leadership. China Fusion Engineering Test Reactor, FEDRA, mission, Bridget here and demo, targeting Q10 by 2035 and net electricity by 2040. Design, hybrid tokamak stellarator configuration, leveraging HTS magnets, 40% stronger than ITER's. 2023 progress, HTS magnet milestone, achieved 25 Tesla fields in prototype coils, world record. Tritium breeding, tested lithium ceramic pebble beds with 95% efficiency at the Hefei Institutes of Physical Science. Strategic investments, funding, $8 billion pledged through 2030, dwarfing EU and US budgets. Global partnerships, collaborates with Russia on neutron shielding. Silent partner in ITER, absorbing technical know-how. Geopolitical implications, energy security, aims to reduce reliance on Middle Eastern oil and Australian lithium. Belt and Road Initiative, plans to export fusion tech to partner nations, e.g., Pakistan, Uzbekistan. Challenges, international distrust, limited data sharing due to dual use, civilian/military, concerns. Domestic pressure, must demonstrate progress ahead of 2035 climate targets. Comparison table, parameter ITER FEDRA US strategy timeline first plasma 2025 first plasma 2030 pilot plant 2035 funding €22 billion, 35 nations, $8 billion, China, $1.8 billion, 2023-2027, Key Tech NBSN magnets HTS magnets public-private hybrids Key takeaways 1. ITER's legacy, proves global collaboration is possible but highlights the need for agile governance. 2. U.S. strategy, bets on private sector innovation and regulatory reform to accelerate timelines. 3. China's ambition, combines massive funding and strategic tech absorption to lead the fusion race. Discussion questions 1. Can Western democracies match China's state-driven fusion investments without compromising open science? 2. How might ITER's knowledge transfer shape geopolitical power dynamics in energy? 3. Should fusion IP be protected or shared globally to ensure equitable access? Visual aid suggestions, map, ITER member contributions versus FEDRA partnerships. Timeline, fusion leadership race, 2023-2040. Infographic, US DOE's funding allocation breakdown. Back cover blurb, from ITER's diplomatic triumphs to China's FEDRA ambitions, this chapter dissects how nations vie to harness the stars and control the future of energy. This chapter underscores the interplay of collaboration, competition, and policy in fusion's global landscape. Let me know if you'd like to explore specific diplomatic tensions or regional energy strategies. Chapter 9, Ethical and Environmental Considerations 9.1 Waste Management, Low Activation Materials versus Fission Byproducts Fusion versus fission waste. Fission, produces long-lived radioactive isotopes, e.g., plutonium-239, half-life 24,000 years, requiring millennia of storage. Fusion, generates low-activation materials from neutron-irradiated reactor components, e.g., tungsten, steel. Most waste decays to safe levels in 100 years. Key materials, tungsten diverters, activated into tungsten-182, half-life, 121 days, and short-lived isotopes. RAFM steels, become cobalt-60, 5.3 years, and manganese-54, 312 days. 2023 advances, Eurofusion's demo, designed with 90% recyclable materials via advanced sorting and smelting. ITER's waste plan, classifies 80% of waste as very low-level, disposable in near-surface facilities. Challenges, tritium contamination, residual tritium in materials complicates recycling, e.g., US NRC limits, 1 Ci/G. Neutron flux, high-energy neutrons, 14 MeV, create deeper activation in structural materials. Future solutions, self-healing alloys, reduce replacement frequency, e.g., tungsten vanadium composites. Advanced recycling, laser ablation to separate tritium from metals, Yukia's 2023 trials. 9.2 Resource equity, tritium sourcing and geopolitical tensions. Tritium supply crisis, current sources, Canada reactors. Canada's 19 reactors produce 2.5 kg/year, phasing out by 2030. Fission liabilities, U.S. tritium reserves, 5 kg, deplete by 2050 without fusion breeding. Fusion breeding, ITER's lithium blankets aim to breed 1.1x tritium consumed, but full self-sufficiency remains unproven. Geopolitical risks, monopolization, China controls 70% of lithium mining, critical for breeding, Canada and Russia hold tritium reserves. Military uses, tritium boosts nuclear weapons yields, incentivizing stockpiling, e.g., U.S. DOE's 2023 purchase of 0.5 kg. 2023 initiatives, tritium recycling, UK's jet reactor recovered 97% of tritium from exhaust in final 2023 experiments. Ethical sourcing, EU's Fusion for Fairness program funds lithium extraction from geothermal brine to avoid mining. Equity solutions, Global Tritium Bank, IAEA proposed reserve for developing nations. Open source breeding tech, Commonwealth Fusion Systems, CFS, pledges to share blanket designs for non-military use. 9.3 Public perception, balancing optimism with realism. Public opinion trends, optimism, 65% of EU citizens support fusion as a climate solution, Eurobarometer 2023. Skepticism, 40% fear another Fukushima due to misinformation about radiation risks. Misconceptions, myth, fusion reactors can melt down. Reality, plasma quenches instantly if containment fails. Myth, fusion solves climate change overnight. Reality, at best, fusion provides 10% of global energy by 2050, IEA Net Zero Roadmap. 2023 outreach efforts, ITER's virtual tours, 1M and visitors explored the tokamak via VR in 2023. TAY's Fusion Futures, school programs in California and Oxfordshire demystify plasma science. Ethical dilemmas, prioritization, should funding favor fusion over urgent renewables, e.g., solar, wind? Transparency, how much should the public know about technical hurdles, e.g., NIF's 5% success rate? Case study, Germany's fusion debate, protests against Wendelstein 7X stem from nuclear stigma, despite zero meltdown risk. Key takeaways. 1. Waste advantage, fusion's waste is less hazardous and shorter lived than fission's, but tritium management remains critical. 2. Resource equity, tritium scarcity and lithium geopolitics threaten global access, ethical frameworks are essential. 3. Public trust, honest communication about fusion's timeline and limits is vital to avoid disillusionment. Discussion questions. 1. Should fusion waste be regulated under nuclear guidelines, or does its lower risk demand new frameworks? 2. Can fusion avoid the resource conflicts that plague fossil fuels and rare earth minerals? 3. How can scientists combat fusion hype without undermining public support? Visual aid suggestions, Figure 9.1, Decay timelines of fusion versus fission waste isotopes. Table 9.1, Tritium reserves and lithium production by country, 2023. Infographic, Public Perception Survey results across regions. Quote, fusion's greatest challenge isn't science, it's ensuring its benefits reach everyone, not just the powerful. Dr. Anika Khan, Research Fellow in Fusion, University of Manchester. This chapter confronts the ethical tightrope of fusion energy, balancing its revolutionary potential against pragmatic environmental and social challenges. Let me know if you'd like to explore specific policies or regional case studies. Chapter 10, The Future of Fusion Energy 10.1 Timelines to Net Energy Gain at Scale, 2030-2050, Key Projects and Milestones, ITER, France, 2025, First Plasma, Hydrogen. 2035, Deuterium Tritium, DT, Experiments targeting Q greater than or equal to 10. 2050 plus, Demo, a successor aiming for net electricity. Spark, USA, CFS, 2026, First Plasma, targeting Q2. 2035, ARC, a modular 250 MW pilot plant. China's CFEDR, 2030, First Plasma. 2040, Net Electricity Goal, leveraging HTS magnets. Challenges, technical, neutron-resistant materials, tritium self-sufficiency. Funding, $20 billion and required globally to bridge R&D and commercialization. Regulatory, streamlined licensing frameworks, e.g., US NRC's 2023 reforms. Comparison table, project timeline key innovation Q target adhere 2035, DT, NBSN magnets, global collaboration 10 Spark 2026, First Plasma, HTS magnets, modular design 211 CFEDR 2040, net power, hybrid tokamak accelerator 10 plus takeaway, while ITER validates science, Spark and CFEDR aim to accelerate commercialization. By 2050, fusion could provide 5-10% of global baseload power. 10.2 Fusion-fission hybrid systems concept, combine fusion neutrons with fission reactors to transmute nuclear waste, convert long-lived isotopes, e.g., plutonium-239, into shorter-lived elements. Boost efficiency, use fusion neutrons to drive subcritical fission, reducing meltdown risks. 2023 initiatives, US DOE's ARPAE, funds * hybrid reactor designs for waste reduction. Russia's T-15MD, tests hybrid blankets for plutonium transmutation. Benefits, waste reduction, potentially cuts nuclear waste lifespan from 100,000 to 500 years. Energy security, enhances uranium utilization, e.g., 100x efficiency gain. Challenges, public perception, stigma from associating fusion with fission. Complexity, dual systems increase engineering and regulatory hurdles. Future outlook, pilot plants, e.g., China's FDS-2, may emerge by 2040, targeting synergy with existing fission infrastructure. 10.3 Space applications, fusion propulsion for deep exploration advantages over chemical rockets, specific impulse, ISP 10,000 plus seconds, versus 450s for chemical rockets, speed, Mars transit in 3 months, versus 7 plus months, 2023 developments, NASA's Direct Fusion Drive, DFD Compact Magnetic Confinement Reactor for crewed missions, Princeton's PFRC-2, tests plasma confinement for in-space propulsion. Concepts, Z-pinch-driven propulsion, helium-pulsed fusion for rapid acceleration. Laser-driven ICF, breakthrough starshot micro-implosions for nanoprobes. Challenges, miniaturization, shrinking reactors to fit spacecraft. Radiation shielding, protecting crews from neutron flux. Timeline, 2035, robotic missions to Saturn's moons. 2050, crewed Mars missions with fusion-powered vessels. Key takeaways 1. Net energy gain, Spark and CFEDR could eclipse ITER's timelines, driven by private sector agility. 2. Hybrid systems, offer near-term waste solutions but require public buy-in. 3. Space frontier, fusion propulsion could redefine interplanetary travel by mid-century. Discussion questions 1. Should fusion hybrids prioritize waste reduction or energy production? 2. Can space agencies ethically justify fusion propulsion's costs amid climate crises? 3. How might fusion success reshape global energy geopolitics? Visual aid suggestions, Figure 10.1, Timeline of fusion milestones, 2030-2050. Table 10.1, Fusion propulsion versus chemical/ion thrusters. Infographic, Fusion fission hybrid reactor schematic. Back cover blurb, * from powering cities to propelling starships, fusion's future is as boundless as the cosmos. This chapter charts the path from lab breakthroughs to interstellar leaps. * This chapter synthesizes technical ambition with pragmatic challenges, framing fusion as a linchpin of humanity's energy and exploratory future. Let me know if you'd like to expand on lunar fuel mining or ethical debates. Appendices - Appendix A, Glossary of fusion terms, alpha particle, a helium nucleus, 2 protons, 2 neutrons, produced in deuterium-tritium fusion, key to self-heating plasmas. Break-even, Q equals 1 when fusion energy output equals external energy input. Diverter, component in a tokamak that removes heat and ash, helium, from the plasma. Field reversed configuration, FRC, a compact plasma shape stabilized by its own magnetic field, used in alternative reactors. Hallraum, a gold cavity used in inertial confinement fusion, ICF, to convert laser light into X-rays. Inertial confinement fusion, ICF fusion achieved by compressing fuel pellets with lasers or particle beams. Lawson criterion, the triple product, density times temperature times confinement time, required for net energy gain. Magnetic confinement, using magnetic fields to contain plasma, e.g., tokamaks, stellarators. Plasma, ionized gas at extreme temperatures where fusion occurs. Q value, ratio of fusion energy output to external energy input, Q1 equals net gain. Stellarator, a twisted magnetic confinement device that avoids plasma current disruptions. Tokamak, toroidal, donut-shaped, magnetic confinement device, the dominant fusion design. Tritium, radioactive hydrogen isotope, H3, used in fusion fuel cycles. Appendix B, Timeline of fusion milestones, 1920-2023, 1920, Arthur Eddington proposes fusion as the sun's energy source. 1934, Ernest Rutherford achieves the first nuclear fusion, deuterium, in a lab. 1951, Lyman Spitzer invents the stellarator at Princeton. 1958, Soviet scientists unveil the first tokamak, T1. 1968, T3 tokamak demonstrates 10 million degree C plasma, sparking global interest. 1983, JET, Joint European Torus, begins operations in the UK. 1991, JET achieves the first controlled deuterium-tritium fusion, producing 1.7 MW. 1997, JET sets a world record Q equals 0.67, 16 MW fusion power. 2006, ITER agreement signed by 35 nations to build the world's largest tokamak. 2013, NIF, National Ignition Facility, achieves fuel gain, energy from fusion exceeds energy absorbed by fuel. 2020, Spark, MIT/CFS, announces high-field superconducting magnets enabling compact reactors. 2022, NIF achieves ignition, Q equals 1.5, a historic net energy gain. 2023, NIF repeats ignition with 2.5 MJ output. Helion Energy signs a fusion power agreement with Microsoft. China's CFETR completes 25 Tesla Heights magnet tests. Appendix C, Directory of Major Fusion Projects and Startups International Projects, ITER, France 500 MW tokamak aiming for Q equals 10 by 2035. Wendelstein 7X, Germany largest stellarator testing steady-state plasma. JET, UK retired in 2023 after 40 years of groundbreaking DT experiments. Private sector startups, Commonwealth Fusion Systems, CFS, USA Spark Tokamak with HTS magnets, Q2 by 2026. Helion Energy, USA pulsed FRC reactors targeting DE3 fusion for Microsoft by 2028. TE Technologies, USA pursues proton-boron fusion with AI-driven plasma control. General Fusion, Canada magnetized target fusion, MTF, with liquid lithium compression. Zap Energy, USA sheared flow Z-pinch reactors partnered with Chevron. First Light Fusion, UK projectile-driven implosion for inertial fusion. National Labs and Research, Princeton Plasma Physics Lab, PPPL, USA pioneers tokamak and stellarator research. National Ignition Facility, NIF, USA laser-driven ICF breakthroughs. K-Star, South Korea Korean artificial sun achieving 100 million degree C plasmas. Emerging concepts, LPP fusion, USA dense plasma focus devices for PB11 fusion. Realta fusion, Switzerland compact stellarators ferromac hybrids. Shine fusion, USA deuterium fusion via piezoelectric crystals. Note, these appendices provide foundational context for readers, linking key terms, historical progress, and active players in fusion energy. Let me know if you'd like to expand entries or add regional/nonprofit initiatives.